Yeah, good afternoon, everyone. Welcome to Module 3. Welcome to Dimensional Analysis and Similarity. This module is going to feel a little bit different than the other stuff we just finished covering. It's a little bit less fundamental. It's less zoomed in, so that's good because I know when you zoom in on a fluid, it gets a little bit unintuitive, but Module 3 is going to be really interesting. So this is an example of a NASA wind tunnel test of an airplane design. So most of what we look at in dimensional analysis and similarity is experimental testing. So we want to figure out how to test scale models properly so that we can generalize results to a full-scale design. So this is, for example, a scale model of some airplane. I'm not sure what scale it is, but it's much smaller. So I would guess it's tough to get the scale from anything in this picture, but I would guess like maybe this wind tunnel, like maybe that's a door on the right there that's open. So this whole wind tunnel is like the height of a person. So this is obviously much smaller than a real airplane, but it's much easier to test. So if we can figure out how to correctly test this, it makes our work a lot easier. Okay, just a review of the points we covered this morning. So we did Navier-Stokes equations, which are basically the governing equations for fluid mechanics. All it is conservation of mass and momentum. It actually is four equations, so continuity plus three components of the momentum equation, and it has four unknowns. So luckily it's a closed system of equations. The four unknowns are the three velocity components and pressure. Talked about how pressure and viscosity create surface forces on a fluid element, and gravity creates a body force. So module 3 is short. I'm planning to end module 3 before reading week, so the midterm will cover modules 1, 2, and 3. So it's only going to be a few lectures long, but I think it's going to be really interesting. I think you're going to find it really interesting. Today we're going to talk about geometric and dynamic similarity. But in this module, we'll talk about common similarity parameters, dimensionless performance parameters, so things that we might want to measure in an experiment. And we'll also talk about Buckingham pi theorem, which is a useful method to take a given problem and figure out which non-dimensional parameters are going to be important for that problem. So what we need to keep constant, what we need to measure. Our learning objectives are to motivate why we want to do dimensional analysis, to define the geometric and dynamic similarity conditions, and to use those to compute test scale parameters based on achieving similarity, which is a fancy way to say if we have some given scale model in a wind tunnel, what does the wind need to be in order to be able to apply the results to the full scale design? Okay. So I'll start with the motivation. The primary motivation of dimensional analysis is to generalize results from an experiment. Here's what I mean by that. So imagine that we're trying to predict the drag force on an airplane experimentally. So one easy way to do that is just put the entire airplane in a wind tunnel that's the size of an airplane and just measure it. Give it a wind speed and just directly measure that drag force. Unfortunately, that can be quite expensive and in some cases dangerous. So what we want to do is test a scale version of that and then generalize that experiment to the full scale airplane. Yes, please.
How often does like scale, if it's like 1 to 10 or 1 to 100, how much does that actually affect the fluid dynamics? Is it like completely 1 to 1? Is it exactly the same like scales?
It's a good question. So the question is how much like does a 1 to 10 scale affect the fluid dynamics? We're going to see basically how to design the experiment so that the fluid dynamics are the same. So if you take your airplane and say you do a say your airplane flies at, I don't know, say you pick a speed of 10 meters per second, very slow. You put that airplane in a wind tunnel at a 100th scale model, and also run it at 10 meters per second, the fluid dynamics will be quite different. That's because the ratio of, say, 10 meters per second for that very small airplane is a lot different than the ratio of 10 meters per second for the very large design case. So we're going to see now how to basically calculate that. So that's the motivation of this part of the course. Any other questions? So what we want to do is generalize and say these results apply not just for our specific scale and flow properties and flow speed. We want to say these generalize to all cases where certain dimensional numbers match the numbers that we had in our experiment. So, for example, applying results from a small scale prototype to, I'll say, a design scale geometry. Okay. So why would we want to test, I guess, a prototype that's a different size than our geometry? Why do we test scale models? I have a list here, but maybe you guys can help brainstorm. So I mentioned a few of them. Yep. Yes. So as Aaron said, testing at full scale is expensive. That's because every time, say, you want to change something in your design, or even just to manufacture the full scale geometry, you have to pay for the full scale geometry. So you're not paying for a small airplane, you're paying for the full airplane. So in terms of materials, manufacturing, all that stuff gets much more complicated when you do full scale. Any other ideas of why we would want to test scale models? Yes, please.
Big wind tunnels are hard to find.
Big wind tunnels are hard to find. So in general, experimental facilities that can fit our full-scale model can be quite hard to come by, and also that comes into the expense. So it costs way more to rent out one of NASA's like full-scale wind tunnels than it does just to figure out how to run a scale model test on like say one of the wind tunnels we have on campus. So there's multiple wind tunnels on campus we have, but none of them can fit a full-scale airplane because you would be able to tell just looking at the building that could fit a full-scale airplane inside it. Any other ideas? Yep.
High speed wind tunnels are often hard to find.
High-speed wind tunnels are even rarer, right? And high-speed conditions on the design scale are really hard to basically mimic. So high speed meaning, say, compressible flows, like you're flying a high Mach number airplane. In order to actually achieve anything that you can generalize from in a wind tunnel, they have very special experimental setups, and they can only run the test for a few seconds. So they have like a super high pressure chamber, and they break a membrane to generate that very high speed flow. So for example, how can you use like a fan to generate like a Mach 4 velocity in like a full scale wind tunnel? It's just like completely impractical. So they have these like really special experimental setups. So high speed tunnels are very, very expensive. Yes.
Do you ever go backwards, like say something's like too hard to really build? Like it's like a I don't know, I can't think of an example, but something that's really small, but you actually want to like be able to really see the scale of it or the fluid dynamics of it, so you make up like an even bigger version, so that
Yeah, I know what you're saying. There's multiple reasons. Like maybe your small geometry is really expensive to make. Maybe you're doing something like a micro scale. This isn't that commonly done, but I guess in principle it could be. If it's really expensive to manufacture something really small, like tight tolerances, you could in principle just test like a bigger version of it and scale the results down. Yep.
Would you ever look at a system or like a component and then just take like different components out and test them individually, or would they always be all
Definitely, yeah.
together and used?
Yeah, so the question is about testing, say, component by component. So sometimes you have to make assumptions to do that, but it's commonly done. So I'm not sure. not sure if the videos I'm going to show are going to be like that, but for example, you can test, say, just the wing of an airplane in the wind tunnel. You kind of have to maybe generalize or assume like we're not going to account for the wing body interactions in this test, but if we're not interested in that, then we can just test the different components. So I would say the answer to that kind of depends. Yep. Aaron? Yes. Yeah. I mean, if you're testing something that's explosive, I guess you'd want to do a scale model test. The other thing is you need more like structural components to hold back, say, the forces. So full scale can be dangerous. So I don't think any of us would want to figure out how to mount an entire, say, Boeing 747 in a wind tunnel and then react to the aerodynamic forces on that because they would be quite high. So you would want to test a scale model because it's a little bit safer and you can mount that in a way that's also less intrusive to the flow. So the amount of structure you would need to actually support that thing in the wind tunnel would probably start interfering with the flow, so your results might not even match. Yes, please. Yeah, that's an interesting one. So it's about the cost of computations, scaling things in CFD. So sometimes it makes basically the analysis simpler in CFD. Some CFD codes, they actually are non-dimensional codes. So the entire code, there's no dimensions. It's all like dimensionless. And then they take the results and they can scale it to different cases by dimensional numbers. So that's kind of a more niche thing. Um, okay. The last one that might not be so obvious is that if we distill the problem into its four dimensionless numbers, we greatly reduce the number of experimental variables. So we'll see it, like for example, for external aerodynamics, the if all you're doing is just changing the density, for example, the density doesn't matter. It's the density's effect on a non-dimensional number. So say the Reynolds number that we looked at, I'm going to talk about that in a second, but it has a lot of variables, right? It's rho, velocity, position, and viscosity. But in fact, that whole thing is just one variable. So we've reduced the problem from four different independent variables to one independent variable. So if we do the analysis right, we're kind of optimizing the number of tests that we have to do. So we're not going to do that in this lecture, but later on I'll give you kind of the Buckingham pi theorem is about how to take this problem that's a function of so many different variables and figure out which key dimensionless numbers apply to that. Okay, so now we'll talk about similarity. So the core, I guess the main reason of all this dimensional analysis is to achieve similarity. So I'll start off with the motivation. So if these two things hold true, so geometrical similarity is satisfied, and dynamic similarity satisfied, then dimensionless performance parameters will match. So in order to be able to generalize the results of your experiment, you have to get the same similarity parameters as your full-scale design. So dimensionless performance parameters, we'll talk about those later, but for example, the lift coefficient and drag coefficient are common ones in aerodynamics. The skin friction coefficient that we saw in the boundary layer was also a dimensionless performance parameter. So there's a whole bunch of different dimensionless performance parameters. And that's what allows us to basically generalize from our design. So we're able to generalize from our test and say if we match, we can generalize to any case where we get those same similarity parameters matching. And we can compute, we don't even have to compute, we just know the dimensionless performance parameters for those cases will be the same. So what do I mean by geometric and dynamic similarity? So geometric similarity. Okay, so same scale in all three dimensions. So it's just a scale model, nothing complicated there. You can't have different scales in different dimensions or else you'll violate geometric similarity. Angles all match as well, so that will happen if you scale it properly. And the flow direction also has to match. So flow direction slash angle matches. These are all intuitive. So you have to blow on your airplane the same way in the wind tunnel that you're going to blow on your airplane in the real world for the results to match. Yes, Ian?
So is there any application where you could scale different axes by different amounts and still get results that you could interpolate in a usable manner?
I'm not really sure of any examples, to be honest. This is normally done, yeah, same scale in all three dimensions. In some cases, you might be able to kind of use like some sort of symmetry in your design to reduce the complexity or eliminate an axis. Like for example, um, you could take your airplane since it's symmetric and just cut it down the middle and then mount it kind of half of an airplane in the wind tunnel. You might get results that are a little bit different because sometimes there's these meandering effects that will be blocked by the wall there. But that's an example where you can sort of simplify the geometry. Yeah, I'm really not sure if anyone else knows of examples where you can scale things and like say you take your airplane and stretch it or something like that in one direction but not the others, then let me know. But it's almost always done the scale in three dimensions. Okay. Okay, so geometric similarity has some interesting consequences. So for example, you need to scale any surface roughness. So for example, your airplane, normally you want to have a very smooth, I guess, paint on the body of your airplane. So if you're testing a scale model of your airplane to achieve full geometric similarity, and you're testing, say, a 1/100th scale or something like that, you have to scale the surface roughness down by 100th as well. So that means your model has to be extremely smooth because your airplane's already quite smooth. So this can, I guess, be a manufacturing issue. You have to scale any fasteners. So for example, rivets. So the rivets on an airplane skin are already quite small. If you're testing a scale model to get full geometric similarity, you have to have scale model rivets in your test. And you also have to scale corner radii. It's kind of a manufacturing thing. So if you have some sort of edge with a certain radius, you have to scale that down as well. So this can be manufacturing challenges for scale models. Any questions about geometric similarity? I'm going through right now the conditions that absolutely have to be satisfied to get similarity, but a lot of the time in the real world, you can kind of assume things away or do your best on some of this stuff. So this is the strict requirements, and my goal is to give you the strict requirements and talk about them, and then we'll talk about all the different ways you can break those rules and that they are broken in reality, okay? So that's geometric similarity. Second one is dynamic similarity. Dynamic similarity requires that you match the relevant dimensionless parameters. So to determine these relevant dimensionless parameters, we're not going to have a way to do that for a couple of lectures. To start off, I'll give you two very common ones that apply in almost every flow. So most common ones. There'll be the Reynolds number and the Mach number. And these parameters are the relevant parameters for external aerodynamics. We'll just say aerodynamics. Okay, so I'll define these numbers here. Actually, I'm going to put this 1 point just for completeness. Use Buckingham pi to determine relevant parameters. Okay. So Buckingham pi is a way that we can do this. I'll talk about the Reynolds number and Mach number. So the Reynolds number, I would say, is the most important non-dimensional number in fluid mechanics. It tells us about the ratio, the following ratio: inertial forces over viscous forces. So turbulence occurs at high Reynolds number because turbulence is caused by these inertial forces. So mixing inertial forces they go up with velocity and size. So yeah, you think of like turbulence, high speed stuff when about inertial forces. And viscous forces are like the small scale dissipations and friction that we saw. So there's two definitions we can go through. So rho UL over mu, and also UL over nu. Okay, so I'll define these variables. So rho is density, we've seen that. U is relevant velocity scale. L is a relevant length scale. I'll talk about those in 1 sec. Mu is dynamic viscosity. Nu is kinematic viscosity. And nu is defined as mu over rho. So with that definition, you can kind of eliminate a variable from your Reynolds number. So these are both two different types of viscosity that we have. And the kinematic viscosity is units of meters squared per seconds, and the other one we've seen before has pascals, seconds units. Okay, so the hardest part I think to understand about the Reynolds number is what are these relevant velocity and length scales. It's going to sound like a trust exercise, but you have to trust that the choice of these is actually a little arbitrary, as long as you choose the same length scales on your full scale design. So if you say the relevant length scale for my airplane is the entire length of my airplane, for both my scale model and my airplane and my full scale airplane, that's okay. You can also say the chord length of the airplane also is a relevant length scale, so that's that. You'll get a different Reynolds number, but since the geometry is scaled, needs to be scaled uniformly for geometrical similarity, the choice of that is actually a little arbitrary. The velocity scale, same thing. As long as you choose the same sort of velocity in your flow, then you get um, the same Reynolds number. Okay, so that's the Reynolds number. We'll do some examples here just to get a little bit more comfortable with that number. The second one is the Mach number, and that is the ratio of the speed of fluid motion over the maximum speed of information. You'll have a better understanding of that after fluids too. This number is just simply U over A. So A is the speed of sound. And the speed of sound is actually a maximum speed of information propagation in our fluid. So sound travels at this speed because the pressure disturbances in the air that cause sound, they're basically information that travels in our flow field. So the pressure, as I'm talking, the pressure perturbations in the air, they travel through the flow field to your ears. That's what sound is. So the maximum speed, for example, you get a shock wave at Mach 1. And that's because, say the plane is traveling and is starting to speed up, the fluid ahead of the plane has enough time to move out of the way. It has enough time to receive the information that the plane is coming. But when you go faster than the speed of sound, the fluid ahead of the plane hasn't actually received the information that the plane is coming yet, so it's shocked by the, and then you get this kind of accumulation of fluid particles right after the shock, and they continue to shock the other fluid particles. That's basically how a shock wave works. Yes? Yep. Yep. A is the speed of sound. Okay, so any questions about these? So we'll say that Mach number of less than 0.3 is incompressible. So basically that means we can neglect compressibility effects. See in fluids too, what this actually is when you have compressibility effects, it's actually a thermodynamic effect in your flow. And if you take a Mach number of 0.3, you get roughly a 10% error in those thermodynamic quantities. So that's where this 0.3 comes from, but I'm not going to do that in this course. Yep.
So when you say like Mach less than 0.3, is that Mach 0.3 if like is that Mach 1? Is that the Mach 1 of that fluid? Like the when
Yeah.
it makes sound that fluid?
Yeah.
Is
So
the like the 0.3 is like comparative to like 30% of the speed of sound.
that's what. Yeah, it's 30% of the speed of sound.
I see the sound of like that fluid.
Yeah, whatever fluid you're in. So in water, like the speed of sound is like 1500 meters per second or something quite fast. So you have a lot before. Water is a little more complicated, but for example, in air, you have 340 meters per second is the speed of sound. So if you travel less than, say, like 100, what would that be, 112, 115 meters per second, you can consider your flow incompressible. But if you start going faster than that, you get compressibility effects, which cause some error in our incompressible flow equations. Okay. Any other questions about that? Yeah. So just to review, in order to match the dimensionless performance parameters we need to have a scale model, geometric similarity, that matches the right dimensionless parameters. So I gave 2 examples here that we'll talk about in this lecture. But for a more general problem, you would need to use or rely on previously people who've done Buckingham Pi for that. Okay, so I gave the examples mostly of wind tunnels, but this also applies to boats. Yep.
If it's like actually like a moving model, if you're using like a turbine or something,
Mm-hmm.
does time scale as well? Like, do you have to like twice the speed of the rotor be like half the size?
Yes, the time also has to be scaled appropriately. So that's a fantastic question because in this video, they're going to show how you need to scale the time as well. So what this video is they test scale models of boats in this massive pool that the US Navy has. And they'll talk about how they basically scale the models in this so that you get equivalent results for a real boat.
Right into that breaking wave. It's there.
Getting up.
Oh,
So they put a
it
rubber
swamped
ducky
it.
in the
That's
pool,
amazing.
basically, but they're
That
gonna.
was right where we wanted it.
Okay.
Now, the real purpose of this facility is not to play with toys or make perfect, unnatural waves. It is to replicate on a small scale the types of waves Navy ships will encounter in the oceans of the world. Research engineers place ships modeled after
Okay, switch off your phones if you're on Wi-Fi, so this will cover. Okay.
toys or make perfect, unnatural waves. It is to replicate on a small scale the types of waves Navy ships will encounter in the oceans of the world. Research engineers place ships modeled after billion-dollar vessels in the water to see how different designs actually behave in real-world conditions.
Right now, this is coming from 45 degrees. It's going to be about a 5-inch significant wave height, which if we were to scale it up for this model would be 20-foot waves. When we're doing a free running model like this, we usually run like a racetrack, like a big circle, or a figure-8 track. So we know the headings that we're running in so that we can correlate that to, the full-scale vessel.
For the model to provide an accurate representation of the real world, a lot of things must be taken into account.
Is the water fresh?
Fresh water.
Okay, not
Yep.
salty.
Nope, fresh water. So when you're in salty water, you're going to have a lot more buoyancy. So when we're ballasting our models, we have to make sure that they take into account that buoyancy difference. So when we go full scale, you're the same conditions.
For fluid mechanics, I always expect that you have to keep the Reynolds number the same as in the real world
one we just
phenomena. But actually, to get the right wave dynamics, you have to use a different scaling, which is based on the Froude number. So the Froude number is a measure of the ratio of inertial to gravitational forces. It's equal to the flow velocity divided by the square root of the acceleration due to gravity times the characteristic length, like the length of the ship.
Okay, so you can do, for example, Buckingham Pi analysis, and the Froude number will come out of that. So then you realize you have to match. That's one of your similarity numbers that you have to match.
In this case, the model ship's hull is 46 times smaller than the real thing, which means to get accurate data, it should be traveling at 1 over the square root of 46 times its real world speed. And to make the footage from the model look the same as that from the full-size ship, you have to slow it down by a factor of the square root of 46, so roughly 6.8 times slower. I'm amazed at just how well these shots match. But of course, that's the idea. Scale the model and the waves so the physics are identical to a real ship out on the open ocean. Naturally,
So that's a really interesting video. I'll post that on Learn if you want to look at it. But that's like the motivation, right? So when they mashed up the videos, they almost look identical. So the non-dimensional performance parameters of this boat will be identical. Okay, so that is one example. There's some other examples here. So this is like a F1 test of a scale model. So this is a car. They actually have a moving ground in this wind tunnel, but it's a scale model test of the car. And they're measuring like
Measure
the
the
velocity
airflow
and the
behind
weight.
a 50%.
So this is, I think, I don't know what scale model. Anyways, so there's another example of like wind tunnel
Could
testing.
confirm their CFD findings in the wind tunnel.
Again, a scale model. So these are the NASA wind tunnels that that are quite interesting as well.
The National Transonic Facility is a fan-driven continuous flow tunnel that injects liquid nitrogen to cool the tunnel down to cryogenic temperatures of negative 250 degrees
So this
Fahrenheit.
is a transonic tunnel, so they're actually worried about the speed of sound now. They're not assuming an incompressible flow, so you have to match the Mach number. So part of the reason that you control the temperature is because you want to control if you're matching the Mach number. So say you're not allowed to change the velocity of the flow, because the velocity of the flow has to be set to match the Reynolds number. And you're not allowed to change the velocity of the flow, so the only thing you can change is the speed of sound. So you have to do that using temperature.
The transonic speed regime encompasses speeds from about 600 to 900 miles per hour. Airflow at these speeds is extremely complex and can behave strangely, making a vehicle difficult to fly. One project at the NTF is the hybrid wing design, a design that would increase fuel efficiency of commercial aircraft by up to 70%.
Okay, let's get that.
The 14 by 22 foot subsonic wind tunnel
So this is a
simulates
subsonic wind tunnel, so you can assume incompressibility now. So in this case, they can just use atmospheric air in the test.
aerodynamic conditions at speeds up.
So this thing that the plane is mounted on, I don't know if you can see my mouse there. That's called a sting. So it's a really fancy device, and they put it behind the plane so it doesn't interfere with the flow under the plane or in front. And um, it can measure like forces in all three directions, and some of them can also measure moments. So it's quite a complicated
Up to
device.
235 miles per hour to test for things like stability and control, acoustics, and basic airflow surveys. Engineers use smoke tests, fluorescent oil, and instruments to better see and measure the airflow on and around the models. Data collected in the 14 by 22 is used in conjunction with computer simulated models to provide a complete picture of the airflow. The 14 by 22 was instrumental in the testing of the low boom flight demonstrator that is intended to achieve a softer sonic thump and in turn commercialize supersonic flight over land. Spacecraft are often tested here as well. NASA Langley's subsonic wind tunnel seeks to understand the behavior of air particles at low speeds in order to develop new aircraft and spacecraft.
So yeah, NASA has a lot of wind tunnels basically. The field trip we're going to go on in a few weeks is to RWDI, so they have a lot of wind tunnels. They're probably one of the most well-equipped like experimental facilities around here. So yeah, they test a lot of buildings and stuff. So we'll see kind of assumptions that they make and talk a little bit more about similarity for their specific problem. Are there any questions about those wind tunnels before I move on? I'm going to do a kind of a numerical example now because we've just talked very generally about this, but any questions? Okay. So let's do an example. Let's do an example from the realm of Formula One. So F1 wind tunnels, or sorry, F1 regulations. Require a maximum model scale of 60%. So in F1, you're not actually allowed to test a full scale car in a wind tunnel. You can only test 60% scale car. So let's see what speed should the tunnel be run at to be dynamically similar to a full scale car at 200 kilometers an hour. Let's say we want to measure the lift coefficient at 200 kilometers an hour on our car. So we need to figure out basically what speed to run the wind tunnel at now. So assuming we could do our geometrical similarity right, so the people who manufacture our model are going to get the scaling all right, we just need to make sure that we match dynamic similarity. Okay, so dynamic similarity means that the Reynolds number of our design, so RED, is the same as the Reynolds number of our test, so RET. Yeah. So the Reynolds number of our design is going to be U design times the length design over new. I'm going to use new. I also am going to give some information on the question. So let's say the car is, the design scale length is 5.63 meters. So it's 5.63 meters long, the full scale car, the design scale. So we can compute the design scale Reynolds numbers now. So 200 kilometers an hour is 56 meters per second times 5.63. And then we'll use air, so 1.48, 10 to the negative 5. That gives us a Reynolds number of 21 million. So the flow is very highly turbulent, is what this means. So this is the Reynolds number our full-scale car is going to be operating at. It's the Reynolds number regime. And usually, if we wanted to be specific, we would add like a Reynolds number L here. So Reynolds number sub L. So we're saying the length-based Reynolds number is this. So in order to basically have the same dimensionless performance parameters, we need to match this Reynolds number in our test. So it's going to be U test, L test over new. So I'm using new in both cases because we can test in air. Say we're testing both cases in just atmospheric air, we're not going to mess with the air and like drop it 200 degrees like NASA does or anything. It's just going to be normal air. So it's going to be the same new. Okay, so that is going to be UT is an unknown. We have 0.6 times 5.63. So that's our LT here. And since we're at 60% scale, the length is just 60% of the full scale length. Over new, and we're going to match the Reynolds number. So that's the dynamic similarity parameter that we'll match. This gives us a test speed of 93.3 meters per second. So it's quite a fast wind tunnel. In comparison, the design speed was 56 meters per second. So since we scaled our model down in the same fluid, we basically decreased L. In order to match the Reynolds number, we have to increase the velocity. So we need more. We lost some inertial forces because we took some length out. So now we need to make up for that by adding more velocity in. Okay, so let's compute now. I said there were two relevant parameters, right? Reynolds number and Mach number. So let's compute the Mach number of the design. (0.16). The Mach number of the test is 0.27. So we're just about to leave that kind of incompressible assumption. So you might notice these two numbers don't match. And this is the problem with testing in air when you're going to be flying in air, is that it's basically impossible to match the Mach number, assuming the air is the same thermodynamic condition. Don't match, but that's okay, because both are incompressible. Granted, the 0.27 is starting to push it with the incompressibility thing, but I gave you 0.3, so you can assume 0.3 in this class. So we can neglect compressibility effects. So that means that any differences in these numbers below 0.3 won't greatly affect our dimensionless performance parameters. Okay, any questions on this example? Let's say now we wanted to test this exact same scale model, but in water. So you can test an aerodynamic device that's going to fly in air, but you can test it in water. You can test it in any fluid you want as long as your similarity parameters match. So place the same model in water. Again, our test Reynolds number has to match our design Reynolds number. I'm going to use a different form of the Reynolds number here, but they are equivalent. We calculate our design Reynolds number up above. It's 2.13, 10 to the 7. So let's plug our water fluid properties in. The length is still 0.6 times 5.63. The viscosity of water is there, so that's mu for water. So if we were to put the same model in water, to get a dynamically similar condition, we would have to run the water at 5 meters per second, 5.6 meters per second. So because the density of water is so much higher than the density of air, we don't have to run it as fast in order to match the Reynolds number. So the core behind all of this is this part here, matching the Reynolds number between your design and test scale. Right? I started every part of the analysis by matching those, and then the rest is just the math. Yes, please.
Design in air and just putting the test in water.
Exactly. Yeah, the design is still in air. Yep.
Your previous Reynolds number not in water, but now you're using the same assumption, but with the test in water, and that gives you a correct estimate of the speed?
Yeah. The Reynolds number is a dimensionless parameter. It has fluid properties in it, but once you combine all that stuff together, as long as you match that Reynolds number, it doesn't matter what fluid your test is in, you can still apply those results to your full scale design, even though it's in a different fluid. Does that make sense? It's very hard to wrap your head around that, I know. That you could test a Formula One car in water and get the same lift coefficient, but that's the physics. So, okay. So, any more questions on this? So the core idea is you have to match all your dimensionless parameters, but certain ones we can start to ignore. Say the Mach number, if both are incompressible, differences in the Mach number can be ignored. I don't have time to finish this example, but the F1 regulations actually set a maximum wind tunnel speed of 50 meters per second. So what that means, hang on, just let me finish verbally. So the maximum wind tunnel speed in the regulations is 50 meters per second, which means there's an upper limit on the speed you can actually match for the full scale design. So you can't actually produce a 200-kilometer-an-hour operating condition in the wind tunnel. You can only produce, the number I got was 108 kilometers an hour because of that maximum wind tunnel speed of 50 meters per second. So that's an interesting case. Any questions? No? Okay, we'll continue this on Monday and have a good weekend, everyone.